In fact, there will be one more lecture this week that will be about degenerate perturbation theory. But since we have enough material, I'm going to not put that in the exam itself. That actually is more important than this one. But that we can always handle in later exams. So, yeah. So, Radharani Tanya is saying, I have made a mistake somewhere in the calculation, right? Is that what you're saying? It's very possible.
Consequence.
Small type on the calculation, there's a question of 0. Should be 3 and not 2. All that is of no consequence in the calculation. Okay, why is it of no consequence in the calculation?
Because the zero term does not play a role into either the wave.
Oh, you mean the Kate zero
Yes.
coefficient. So when A plus A dagger holds a 4 acts on it, Kate zero coefficient should be 3 and not 2. Quite possible. I may have made a mistake there. But you will have to check for sure. I'm not sure which one you're referring to. Are you referring to this? Are you referring to this direct calculation or?
No, sir, the M sandwich.
The M.
Even that is fine, sir. I mean, like, M doesn't matter. It just adds a delta.
Okay. No, it may not matter because I know the final result is right because that's a very standard result. However, I may very well have made a mistake somewhere in the middle of the calculation. But that's good. Then you should check even with, work it out yourself anyway. Right. So before we start officially, are there any questions?
Sir, in
Yeah.
lecture 2, you
that's
gave an
variational, right?
Yes, sir, variational. At the
Yeah.
end, you gave an argument to just to establish the virial theorem. So I was asking, can we actually use the virial theorem to calculate the ground state or something like that?
You can, no, the virial theorem essentially gives you the relationship between expectation values of the kinetic energy and the potential energy, right? But only for actual states. So it depends on what you mean by what you're saying. For example, in the hydrogen atom problem, the virial theorem will tell you that the expectation value of kinetic energy for Kepler will definitely be minus half times the expectation value of the potential energy. And therefore, you can easily figure out that if you add the two together, kinetic and potential, you definitely get the expectation value of the Hamiltonian, right? So if you add these two things together, you're definitely going to get negative of the expression value of the potential energy, right? So basically what you can say, am I right about this? No, I'm not right.
So
T
should be
is
plus V by
the other
2.
way around. It should be, is that right? No, that makes no sense whatsoever. Let's work it out and not try to be too clever. It's expression value of T plus expression value of V. So it's of course going to be half of expression of V or minus half of expression value of T. So this much is correct. But if you know one of them, you can use it to calculate the rest. But how would you use this to calculate the expression value of any one thing without knowing the rest? That's not very clear to me.
So suppose I start with a family of wave functions.
That's okay. That's what I was worried about. You were saying, can you use this for a family of wave functions? For example, can you just calculate, let's say, the kinetic energy and dispense with the calculation of the potential energy simply because you can use, well, this is only for Kepler, but in general, if it's a homogeneous, remember, virial only works for homogeneous potentials. But if you have a homogeneous potential, the rule is twice expression of T is nu times this. Okay, that's the virial theorem, where nu is the degree of the homogeneous function which the potential is. Now, what you are saying is, suppose I calculate the expression value of kinetic energy by simply calculating d psi dx and then squaring that and integrating. Of course, halving it and multiplying by h cross square by m if you want to. Having said all, and then can I use this to calculate expression value of v, and then use that result in calculating the energy expectation value, and use that to do variational calculation. It should be pretty obvious to you that you can't. Can you see why? If you try doing this, you will run into a very obvious problem. The problem will be that the expression of the Hamiltonian, which is expression of t plus v, of course, always, will turn out to be, this is 1 plus 2 by nu times expectation value of t, right? It will be directly proportional to the expectation value of t, correct? And since in most calculations, whatever family of wave functions you choose, the expectation value of t will come out to be something like, say, for the Gaussian case, this just comes out to be proportional to alpha. Some other thing is, so there is no extremum in this expression, right? Note that even for the harmonic oscillator problem, the variational method worked because when you did the calculation, expectation of t came out to be proportional to alpha, potential energy came out to be like 1 by alpha, so you had an extremum. There were two terms, one was increasing, the other was decreasing, and somewhere in the middle you could get a minimum. But if this were your correct expression for the variational family, and you try to do it do variation with this, then of course it will not work out, because you will end up with this nu, of course, is a constant which depends only on the potential, on the nature of the potential. So that's a fixed quantity. So thing in the bracket here is fixed. And expectation value of t depending, of course, depends on your family of wave functions. But if you say take a Gaussian family, which is a very common choice, you would end up with something proportional to alpha, always, and that would never have an extremum. But can you see why that is wrong? And I don't really want to have a conversation with only one person. Are the rest of you following what is exactly being tried here? That's one thing. Why, if you could do this, it would be a great thing, because it would make my life a lot easier in doing calculations. And finally, why is life not so easy? Why can't you do this? These are 3 points. One, what am I doing? If I could do what I was trying to do here, what would the advantage be, and why I can't? So is there any confusion about these questions? Last one we have not talked about yet, but the other two. Let me just remind you that the virial theorem only works if you have potentials which behave like this. Homogeneous potentials. And this theorem, of course, can be worked out in many ways, not just using variational. But the theorem really says that for any such homogeneous potential, the expectation value of kinetic energy and that of potential energy is related by this connection. So if you calculate one of the expectation values, you can use it to calculate the other ones. But I'm trying to say that if you really tried that, say, while calculating for the variational family of wave functions, you must be making a mistake, because it would be nice if you could do it, but you must not be able to, because if you did it, then the variational method simply wouldn't work.
So this works only when the family of wave functions contain the eigenfunction. So if we previously know the eigenfunction, then
well, not exactly. You're close.
It works only when it is the correct eigenstate.
Exactly. This works only when it is the eigenfunction, not even when the family contains it. If you follow the argument I made here, say for the harmonic oscillator, if I just use this, for harmonic oscillator, what is the value of nu? Nu equals how much?
2.
2, right? Because half kx square, or half m omega square x square. If you replace x by kx, the potential gets multiplied by k square. So that's mu equals 2. And this immediately gives us one of our very familiar old results, that the kinetic and potential energy expectation values for the harmonic oscillator are equal. This, by the way, also works in classical mechanics. The average value of kinetic energy and the average value of potential energy are equal for SHO. Not only that, it works also for statistical mechanics for similar reasons, which is why you have half kT for the kinetic energy, half kT for the potential energy when you're talking of a vibrational degree of freedom. Half kT each, because both the potential and the kinetic energy contribute the same amount. Okay, so if I did the harmonic oscillator, if I tried working the harmonic oscillator out with this family of wave functions, okay, normalize this 4th root of alpha by pi and so on, and take this family, we know that alpha equal to 1 is actually the ground state wave function. So this family of wave functions actually contain the exact energy eigenfunction, but that's simply because we have chosen a very simple problem where we know the answer. In general, we will not be so lucky. But no matter what, if I tried calculating with this, what will this tell me? Kinetic energy turns out proportional to alpha. Potential energy, proportional to alpha again. Because since they're equal, when you add them together, you get an expression which is a multiple of alpha. Now, if that had been correct, that's not correct, by the way, but if that had been correct, then the variational method simply wouldn't have worked, because then it would have predicted that the minimum value of the total energy occurs for alpha equals minus infinity, which is not even allowed. Or say, if you just stick to, wait, just hold on. Okay, so if this were a correct calculation, I hope I have unmuted. Yeah, I have unmuted myself. If this were the correct calculation, then the variational method simply wouldn't have given you a bound. But you know it does. It gives you the exact bound. But the correct thing is, you cannot do this calculation this way unless you're actually at an eigenfunction. Not even if the family contains it. This works only for the eigenfunction, not for other values. Okay, next. Okay, if there are no questions, let me just start on a new topic. Okay, not really a new topic. I just wanted to, could you explain intermediate normalization? Oh, the idea was basically this. You have a wave. So just to remind you, the background for the theory is you have H equals H0 plus V. H0 is exactly solvable. V is small in some sense. And we want to find out the solutions to this equation. H psi equal to E psi. And when we wrote out the solution in a form of a series, a formal form of a series, where we said, okay, we first put in a parameter here. We just introduce a lambda by hand so that we can keep track of how many powers of V we are dealing with. And if V is small, higher powers of V should give you a small contribution. That's the idea that we are using. And then we wrote psi lambda equals psi 0 plus lambda And the energy eigenvalue for this particular Hamiltonian, which is h of lambda now, will be E0 plus lambda times E1. Okay, let's be consistent. And then we wrote down this equation H0 plus lambda V times chi lambda equals E of lambda chi lambda, and matched powers of lambda on both sides. That's how perturbation theory works. So basically what you end up with is something like this. You end up with, first of all, the first equation that you end up with is always this equation. Which is nothing but the Eigen equation for H0. And this immediately tells me that the ket psi 0 has to be an eigenfunction or eigenket of H0, and E0 has to be an eigenvalue of H0. So E0 has to be one of the possible eigenvalues. And let's say we just are looking at the nth one. So E0 has to be epsilon n. And then comes the point that if epsilon n is non-degenerate, then we are sure that psi 0 has to be the corresponding eigenket. So this is where the non-degenerate nature of that we are assuming at this stage comes in. Degenerate perturbation theory is a bit more complicated, because in non-degenerate perturbation theory, we know where we are starting from. If you say that, okay, we are trying to find out how much the nth unperturbed energy eigenvalue shifts, if that nth unperturbed eigenvalue happens to be non-degenerate, then we are sure what our ground wave function is, at least for lambda equal to 0. We know psi 0 is definitely phi n. And then we try calculating the first order correction, second order correction, and so on. And how we do that is exactly what we described in the way this perturbation theory calculations are done. Okay. And as a consequence, or while doing these calculations, we also get the first order, second order energy corrections. Fine, but now we come to the point of this normalization. What we are getting here is psi lambda Okay. Now, once we can calculate psi 1, psi 2, etc. from here, this of course gives me an expression for psi as a function of lambda. And we know that ultimately we will put lambda equal to 1, and that will be my perturbed eigenfunction. At least that's our hope. Okay. Now, if, for example, we could calculate explicitly psi 1, psi 2, and all these corrections, that is, if the perturbation theory formally told us exactly what psi 1, psi 2, etc. are going to be, then I've got this psi lambda as a function of lambda. Or if I put in 1, I get the value explicitly for the ket psi for the full theory. And then the question of any normalization convention simply will not arise. Simply because I know I have got the full ket in my hands. If it turns out to be normalized, fine. If it does not turn out to be normalized, there's nothing much I can do about it. It's still done. It's a given expression. Of course, if it is not normalized, I can then normalize it to talk about to simplify calculations. Or frankly, we don't have to. We can perfectly well deal with unnormalized eigenkets and work with that. So is there any confusion so far? Yes? So this part is clear, fine. Okay, so now that the real problem is, of course, or not really a problem, but what looks like a problem at this stage at least, is that Kate Shy one, if you want to calculate it from perturbation theory, it seems perfectly nice. You get, okay, I may be getting the sign wrong here, so you have to be a bit careful about that. So this is what Kate Shy one looks like. Okay, except that this piece, whatever coefficient you have here, you can get no information about it whatsoever from the perturbation theoretic calculation. Perturbation theory, the equations don't tell you how much this coefficient is. Okay, so you are actually free to put in whatever you want here. So again, is this part clear to everybody? Yes? Okay, when I say everybody, okay, if anybody else has a confusion here, please speak up. But anyway, this is something which follows from the structure of the theory that you cannot find out this part. And when you go on to calculate Psi2, you will find that there are more things you cannot find out explicitly from the formulae, partly because of the fact that you don't exactly know what this quantity is, partly because of new unknowns come up in that stage, at the second order stage. Okay, so basically your psi of lambda is not completely known. This, okay, I don't really need to write it again. In this part is exactly known. I know it's phi n. I almost know all of this, but there is a part which is a multiple of phi n which I don't know, plus of course this piece which I do know. Similarly, at the lambda square order, there is a part which I will not know. There is a part which following that, which I do know explicitly. Okay. So since psi lambda is not explicitly known, the question of whether it is normalized or not arises. Or at least you have a choice there. If psi lambda were explicitly known, then its normalization would have been whatever it is. You just calculate it, you get something. If you get 1, you're lucky, but if you don't get 1, you have to live with it. Here, psi lambda may not be, is not completely known, so now you have a choice. Okay. Now you can choose to make your life easier by saying, okay, trying to figure out how much this is going to be and fixing it as something simple. One choice is to insist that psi lambda is going to be chosen to be normalized for all values of lambda. Not just for lambda equal to 0, which it already is, because psi 0 is phi n, which is a normalized wave ket. Or I'm not even demanding that it's 1 for lambda equal to 1, which is the final answer. We want psi lambda to be normalized for all values of lambda. That's a choice. Do you have to make it? The answer is no. But that is one of the standard choices you can make. Okay. But another choice could be that we make life simpler for ourselves by choosing this. Note that what don't we say, and let's just talk about the first order calculation. The thing actually works even for higher orders, but for the time being, let's stick to just the first order thing. The zeroth order term I know is phi n. Then at the lambda order, I have this term. This is something I don't know. Plus, of course, I know this piece, Vmn. And then, of course, there are lambda square order terms. Okay. Now, what do you think will be the simplest thing for me to do? This unknown quantity. What would make life easiest for us? Yes. 0. The easiest would be to just make it the easiest possible thing, make it 0. And how do you ensure that it's 0? You essentially demand the psi n1 is orthogonal to phi n, the unperturbed wave function. Note that this piece, of course, you don't have any choice here. This is whatever it is. Okay. If you want to make the bracket vanish, this unknown term, this is the only one where you have a choice. So the choice you are making is, okay, I demand this works, that whatever extra piece comes in, psi n, not only psi n1, psi n at any order, psi n2, the demand is orthogonal to phi n, and so on. So this is what is called intermediate normalization. You demand that the correction terms are orthogonal to the unperturbed ket. Why do you do that? The answer is it makes your life slightly easier. At least some of the calculations, some of these nasty looking terms drop out. But this should leave you with a nagging feeling that it's not really a choice of normalization like the way we usually do. Like, for example, in a wave function, in a situation like this, whether you're talking of phi n or the I alpha phi n does not matter. Both physically mean the same thing. Now, that actually dropping this or choosing it, giving it an arbitrary value, keeping it and giving it some value, that it does not make a difference to the final calculations, that's not so easy to see. That takes a lot of effort to work out. Okay. It so turns out that these unknowns will not have any effect. We have just shown, we did show that for En2. By the way, in lecture 3, I did a second order energy correction calculation, which is actually more complicated than what you would see in most books. Why? Because in most books, you simply start by assuming that this term is not there. That is, what they are really doing is intermediate normalization. They just may not be telling you that. Okay. If you do that, you don't have to worry about an unknown piece. And then if you calculate En2, you get an expression. That expression is right, because ultimately the expression for En2, the second order energy correction, and the third order and the fourth order energy corrections, these quantities will not depend on these unknowable quantities. The physically knowable quantities, things which actually can be measured or can be at least indirectly measured in physics, in physical experiments, those quantities are not affected by your lack of knowledge here. That you can show rigorously, but showing that rigorously for all potentials is a non-trivial task. But what I did do is keep this quantity in. I called it some alpha or something, whatever, lambda alpha phi n here. Did not assume it's 0. Just went on to show that no matter what, you are going to get En2 expression where the alpha will not be there in the final result. Okay. So that was essentially done primarily to sort of drive home the fact that there is something that you cannot figure out from perturbation theory, but also that inability to figure something out will not affect your calculation in the long run. Well, you might say energy eigenvalues are just a small part. Why not? Can't this extra piece show up somewhere else? Like, say, if we are trying to calculate, say, the position expectation value in the state psi, there won't be show up. Okay, let me assure you that this quantity will not show up at all, at least to the relevant order of lambda. Any corrections due to this will occur at higher powers of lambda, but that will come in only because you have truncated your series and you have not taken the full calculation. So ultimately, this quantity, this ignorance, if I can call it that, does not matter. Okay. But the intermediate normalization is simply a choice. You make the simple choice that these unknown things are just 0. And the formal way to say that you demand that every correction that you have to your unperturbed wave function is orthogonal to the unperturbed wave function. That makes subsequent equations very easy. But that also sometimes leads to trouble in the sense that at least the fact that this quantity which could be there is not affecting any physical result, that is not at all obvious, because you have started by choosing it to be 0 anyway. So most textbooks will actually not even mention this, but this is something which really is there, and you have to be worried about it sometimes. Okay, Bonali, is that a good enough answer to the question that you asked? So, anything further? By the way, the mid-sem actual syllabus, of course, is the full thing, right? Everything that has been done till date in the class, except, as I said, the 2s+1 rule will not be there. Okay, so nobody seems to have any questions. So let me just ask a few. I know that most of you may not have had time to look at today's video, but in today's video that was uploaded a while ago, some of you may have, because that, apart from some editing, the video I put up today is the same that I used last year. Okay, the last one has an extra piece. This one, that is lecture 3, had an extra piece which I put in, which you can easily make out because it was written using this tab, and that was lecture 3. Lecture 4 is exactly what I put up last time. So some of you had already seen it then. But anyway, you may have definitely forgotten, and you definitely need to see it again. Let me just point out that in the only important part as far as the exam is concerned is this calculation that I outlined there, which is p square by twice. The Hamiltonian is p square by twice m plus half m omega square x square plus something like this. I don't remember whether I had a 4 factorial there in my formula or not, but anyway, this is of course H0, the harmonic oscillator Hamiltonian, and this is the potential. And because the potential already has a lambda in it, you can treat that lambda. You can just either supply the, remember the only role that this parameter lambda plays, whether you call it lambda or not is unimportant, but that parameter that I put in the perturbation theory, the real role for that is that it helps you to keep track of how many powers of the potential is appearing in a term. And since potential itself comes in handy with an extra factor, I may just forget about putting in an extra lambda. I could just use this as the perturbation parameter, and it would work fine. So ultimately what will happen is you will get an energy expression for the anharmonic oscillator, and our claim was it will be of the form E0 plus lambda E1 plus lambda square E2 and so on. So this looks formally at least like a Taylor series expansion in lambda. Okay, and E0 of course is the unperturbed energy eigenvalue for whichever state you're talking about. If you're talking of the ground state, you don't have to. You can talk of an excited state equally well. But I worked out the ground state in the video, but you could do it for any other state. But for the ground state, of course, this will be half h cross omega, unperturbed energy eigenvalue, plus first order correction, second order correction, and so on. Now, let me just tell you something which may sound like a, well, sound very bad at the face of it. Okay, any guesses about the this is a power series, right? So can you guess what the radius of convergence of this power series is? Yes? So Shayan is saying mod lambda less than 1. Anybody with a tighter bound? Of course, the answer is correct in the sense that that's not the radius of convergence. Do you mean the radius of convergence is 1, or do you mean mod lambda less than radius of convergence is less than 1?
Sir, I don't know it.
No,
I
you
don't
mean
know.
when you say mod lambda less than 1, are you
Yes,
saying
it
radius
is
of
less
convergence
than
is 1?
1. Less
Okay.
than 1. I mean, radius of convergence is 1, but it is not convergent on the boundary.
So that's possible. That's very much possible. So that's what your guess is. Anybody with a tighter guess for a smaller value of lambda? Okay, let me give you the answer to this. The answer to this is this, but of course, like every power series, there's a power series in lambda, and like every power series, it must have a radius of convergence, right? And the radius of convergence for this power series is the smallest possible radius of convergence that any power series can have. What is that?
0.
What is the smallest possible radius of convergence for a power series? Yes? Come on, you should know this. Okay, Rajrubai is saying 0. Yeah. And the radius of convergence of this power series is exactly 0. What that means is that if you were to treat this as a power series, this would simply not give you anything useful. That is, the idea may seem like, okay, if I calculate enough terms, in fact, in principle, you can, for this particular problem, there are algorithmic ways of calculating any En, no matter how high you want. That is, any order correction you can calculate. And lots and lots of people have spent a lot of time trying to figure out better and better ways of getting higher and higher order terms. So in principle, I can safely say that I know the entire series. You may not know anything beyond the first two terms, the ones which we have done in the video. But in principle, we can figure out every one of the terms in the series, and not only in principle, people have actually figured out efficient ways of calculating higher and higher order terms of the series. However, knowing these terms of the series may not really be as good as it seems at first sight, simply because if your series has a radius of convergence of 0, what that means is that any non-zero lambda, forget 1, any non-zero lambda is going to make your series diverge, which means the series will not make sense apparently. Okay. So, question: can any sense be made out of such a series? That's number one. But number two, let's answer number two first. How do I know that the radius of convergence of this series is 0? Now I can prove that explicitly if I could find out a formula for En, and actually you can find out enough about En to show explicitly by direct calculation that the radius of convergence for this series is 0. Radharani is saying E is not bounded. Well, E is not bound. When you say E is not bounded, what do you really mean? For a given lambda, is E not bounded? That would be disastrous, right? The potential energy keeps on rising. So the potential energy keeps on rising anyway, even for the harmonic oscillator. But that tells you that you can have arbitrarily high energy for bound states. But a given energy level, of course, is bounded, and it has a well-defined energy. So when you say E is not bounded, what exactly do you mean by that? By the way, this is not always this is not the case for every perturbation series. You already know one perturbation theory where the radius of convergence is infinite. Can anybody tell me an example? Give me an example of a potential where the radius of convergence is infinity. That means no matter what the coupling constant is or what the size of the potential is, it's going to converge. So, okay, let's talk about this problem. The Sharon is saying shifted harmonic oscillator. Yeah, well, basically the problem that we solved in lecture 3, which is this. This, of course, was an artificial problem. H0 is a harmonic oscillator. Well, it's easy to see that even H is a harmonic oscillator just with a shifted value of the frequency. And we know what the energy is for this explicitly. Energy E is half has to be, because this is just a harmonic oscillator with a frequency which is square root of omega square plus alpha square, right? So I know the exact value for this energy, and if you were to calculate this term by term, you will just reproduce the terms in this series, and you are going to simply get a series which converges no matter how big alpha is. Okay, and it converges to exactly this expression. So this actually has a radius of convergence which is very, very big. So it's not true that all perturbation theory series will not have a finite radius of convergence. But in our case, this problem now, the reason why I know that this cannot have a non-zero radius of convergence is very simple. Okay, and this is something which again falls back on complex analysis. Remember, convergence issues are best treated, especially for power series. Convergence issues are best treated in using complex numbers. Just hold on. Okay, sorry about that. I hope I'm still here. I think so. So what I was saying is this. When a power series converges, remember a power series is always a series of something like z minus z0 to the n Cn. And going from 0 to infinity, right? And the radius of convergence essentially is this notion that the power series will converge whenever mod of z minus z0 is less than r. So there will be some r for the series, always. And diverge whenever mod z minus z0 is greater than r. And at z mod z minus z0 equal to r, that depends on the specific series. For some series, it may diverge everywhere on the boundary. For some other series, it may converge everywhere on the boundary. For some other series, it may diverge partly or converge partly. But within the disk, in the interior of the disk, it's going to converge. Exterior is going to diverge. And for us, of course, if you're thinking in terms of lambda, our power series is centered at 0. So if it had a non-zero radius of convergence, so it would converge for all values of lambda inside this disk, right? Whatever the radius of this disk is. Maybe very small, but if it's at least non-zero, some finite value, it will converge everywhere inside and give you the energy eigenvalue for any value of this thing. Okay, so can anybody see why there's a contradiction between contradiction there? That is, the fact that it converges for all values in this disk. Why should that be a problem? Yes.
Sir, are we allowed to consider non-Hermitian Hamiltonians?
You mean if lambda is complex, then you're going to go to non-Hermitian Hamiltonians? Maybe not, right?
Yes.
So,
Sir, I'm asking, is that allowed?
well, it is. There is a huge branch of study where you deal with non-Hermitian Hamiltonians. We are simply not doing it now. And non-Hermitian Hamiltonians have their own very special role to play, both in mathematical physics, also in some other cases like study of decays and so on. For the time being, we are not doing that. So lambda has to be real. But the theory of convergence says that if it converges somewhere, it has to converge within a disk in the complex plane. So that has nothing to do with whether lambda is real or not. And it should be obvious what that issue is. And once you realize that, you would realize also that the statement I made about this Hamiltonian is actually wrong. This does not converge for arbitrary values of alpha. As a perturbation theory here. There is an upper bound here. But this one, you should be able to figure out first. I am claiming that such a radius of convergence, such a disk of convergence, where for every value of lambda inside this disk, this perturbation series converges and gives you a value for E, would be impossible to have. Can you see why? Okay. Now, I'm not interested in what happens when you move away from the real axis. So the fact that the series converges here, I have no problems with. If it had not converged here or converged here, I don't care. I only care for real values of lambda. But can't you see that there would be a problem? Okay, first of all, this potential that you have, where is this potential minimum? Can anybody tell me that? Yes?
0.
0 meaning x equal to 0, right?
Yes.
And the value is also 0 there.
Yes.
Are you sure? So what you're trying to say is the potential sort of starts off looking like a parabola, because for very small x, of course, x to the 4 is even smaller, and then becomes sharper than a parabola simply because of the x to the 4 term. It sort of begins looking like a parabola, then it becomes steeper. But it's, of course, a smooth curve. Just steeper than a parabola for large x. Yes?
So if lambda is negative, then it is minimum away from the origin.
If lambda is negative, it's minimum away from the origin. Are you sure? You have pointed out a problem, but your answer is wrong there. If lambda is, even if lambda is negative, for very small values of x, the potential energy is going to behave like x square. Right? It has to. X of 4 is very tiny there. So for very small values of x, you always have a parabola like this. But if lambda is negative, what is going to happen for large values of x?
So it is going to go to minus infinity.
Yeah, the series function is going to look like this. And what that means is that this system will have no bound state possibly. For negative lambda, this simply can't have a bound state, no matter how small the negative lambda is. Because no matter how small the negative lambda is, the presence of a lambda by 4 factorial x of 4 term for large enough values will ensure that for large enough values of x, the potential is going to diverge to minus infinity. And such systems simply cannot have a ground state. There is no lowest possible energy level here. So now can you see the problem with this? The point is the perturbation series is a power series. So if the power series converges for some positive value here, maybe some very small positive value, but positive value, then automatically it would have to converge at the negative of that value. There's no way you can stop that. Okay? Simply because of this convergence disk thing. I may not worry about what happens when you are moving away from the real axis, but this will at least tell me that for a negative lambda also it will converge. And that is simply impossible. Right? So, because then you would end up with a shifted ground state energy level for a potential which looks like this, which does not have a ground state at all. So this simple calculation shows, okay, there are more rigorous ways of putting it, but this simple argument tells you that if the perturbation series for the quartic anharmonicity actually had a finite non-zero radius of convergence, it would give you completely nonsensical results about negative lambda. And that is simply something which can't happen. So you end up with the conclusion that the only value of lambda for which this series as a whole will converge is for lambda equal to 0. And that's the radius of convergence 0 thing. By the way, a power series has to converge at 0, at z minus z0 equal to 0, because when z minus z0 is 0, all the powers simply drop off. Only the constant term remains. So that radius of convergence always has to be there. But you can't have anything more than that. So there is something rather disturbing about this, because all the calculations we did, we sort of justified them in our minds by saying, okay, ultimately we are only calculating the lowest orders, but because the potential is small, that higher and higher order terms are going to be small. So if you push it to high enough order, I'm going to get more. So if I want more accurate results, I will just push it to higher order and I will get more and more accurate results. And I'm done. So if I do a first order calculation, I don't get accurate enough results, I will do a second order calculation, then I will do a third order, then I will do a fourth order. And in principle, by pushing it order higher and higher to better and better orders of accuracy, I will be able to calculate the result as accurately as I want. Maybe with a lot of effort, but we can do it. That was the basic idea that at least plays on the backs of everybody's minds when they start the perturbation theoretic calculation. The problem there is, if you look at this rigorously mathematically, for most non-trivial perturbations, this will never work. At least, it's not this will never work. This idea that the series will converge, and hence I can get better and better results just by taking more and more orders, is simply wrong. Now, that doesn't mean that the perturbation series is useless. The perturbation series is very, very useful. Why is it useful? It's something which most physics courses sort of sweep under the carpet a bit, because it requires some advanced mathematical training which usually physicists don't get, at least at the beginning. And I'm not going to give you the full explanation for this. And I'm definitely not going to do it today, because I don't want you to sort of want to bother you with this new thing before the exam. So right in the first class after the exam, we will take a deeper look into the nature of this series. The fact that this series is really not a convergent series, is something which is called an asymptotic series. It's a bit strange that physicists don't learn much more about asymptotic series, simply because many of the calculations we do actually involve asymptotic series. And how would you get reasonable answers, even very accurate answers, out of series which don't converge? That actually is a very important branch of calculations which physicists do. Sometimes physicists do this without even understanding that they are doing something like this, but at least without going to the mathematical background necessary, because physics sort of naturally leads you to this. But this kind of series is actually everywhere in physics, so we need to at least know a bit about it. Not necessarily the full mathematical theory, but at least what exactly does this mean. So we will talk about this in the first class we will have after the midterm. But this is something you have to be aware of, that you can't blindly just keep on adding order by order and expect everything to fall in place. And by the way, that is not to say that taking more and more terms is actually useless.
Excuse me, sir.
Yeah.
So, but if we do have a positive lambda,
Just hold on. I have a call coming in. I will just attend to that and talk to you. Okay, I'm back. So what were you asking?
sir, suppose if lambda is indeed positive,
Mm-hmm.
will these series finally converge? Because I mean, earlier I was mistaken thinking that E1 and E2 correspond to some different things. But if they are just corrections, then won't they reduce if lambda is positive and won't the series converge?
No, the point is, if lambda is positive and the series converges, first of all, I guess let me just make this clear. Okay, let me put those upstairs the way I was writing it in the slides. I'm claiming that the actual energy E is E0 plus lambda E1 plus lambda square E2. These are just correction terms, right? And if this series, the infinite series, actually converges for positive lambda, would there be a problem? The answer is it would not be a problem if it converges for positive lambda. But it's the very nature of power series that if it converges for positive lambda, it also has to converge for the same value of negative lambda, or at least a value just smaller than that in size. Is that okay? Is that point clear?
Yes.
And then you will end up with this contradictory thing that you are ending up, your formula is telling you that for a negative lambda, you are going to end up with this particular value of the energy for, say, the ground state, which simply cannot be correct. Okay? Because this particular potential has no ground state. It's not possible for this to have a bound ground state. Okay. So that is where the contradiction is. The contradiction simply lies in the fact that if it were to converge for a positive lambda, it would also have to converge for a negative lambda. And that is simply not allowed. So this is basically a proof by contradiction. If you assume it converges for a constant lambda, you end up with it also converging for a negative lambda. And that is where the contradiction is. Okay? Is that clear?
Yes.
And that's because it's a power series. And power series always behave that way. That is, this mod z minus z0 less than some r, and you will always get a convergence. Okay, and having said that, let's go back to this. The other Hamiltonian that we talked about, H equal to and let's put in a lambda, some perturbation parameter lambda here. And I get a power series in lambda for E of lambda. Can anybody tell me what is the value of lambda? What is the radius of convergence for this power series? It's not infinite. I made a mistake when I said it's infinite. It's not. Can anybody tell me what is the value of the radius of convergence here?
Omega square by alpha square.
What?
Omega square by alpha square.
Why do you say so?
Beyond it, the expression would become negative, so no ground states.
Good. That is, if lambda went beyond minus omega square by alpha square, then the potential will end up not being a harmonic oscillator potential, but an inverted harmonic oscillator potential. Right? That's what you are saying. If lambda is less than minus omega square by alpha square, or less than equal to, then of course the series simply cannot converge. This is something you can easily figure out also from the fact that the series is really a series for this. Right? And you know that a binomial coefficient series will only in fractional powers will only converge. So this is series which looks like omega into square root of 1 plus lambda alpha square by omega square. So by looking at the exact answer here, you can easily figure out that it will converge only when lambda alpha square by omega square is less than 1. Or the physical argument is if lambda were less than minus omega square by alpha square, this would definitely not converge. This cannot converge because then this series, this potential will not have a ground state then. And from that, you conclude that the power series, if it has to converge for omega square by alpha square or less. Right? Once again, the same thing. If lambda diverges when you are below minus omega square by alpha square, it also has to diverge when you are above plus omega square by alpha square. Once you are outside the radius of convergence, you are going to diverge. in both directions, in all directions actually. I'm saying both directions because we are just interested in what happens on the real line. But actually, this is a complex series in principle. So the convergence is about moving in any direction. The furthest you can go from the center is the radius of convergence. Any further, you're going to get divergence in whichever direction. Okay. So there is a bit of a, well, I might say we cheated you a bit when we talked about the perturbation series. Not really, because all we did was we never actually assumed that it's a convergence series. We just said it's a formal series. The only role of lambda is to keep track of how many powers of the potential is coming in. However, you might be right to feel cheated a bit, because the implication there was if you do correct calculations for low orders, that's enough, because higher order terms have more potentials, and more potentials means smaller and smaller contributions, and smaller contributions simply means that ultimately you can ignore them. That ultimately you can ignore them is actually correct, but it's correct in a very different sense from the way in which we have stated it. So we will explore this mathematical issue about how to handle asymptotic series. What numbers you can, what do these coefficients actually tell you, the coefficients of the series that you're getting, the E1, E2, etc. And can you get useful information out of this? But we will do that after the break. We will not go deep into the theory of asymptotic series. That will depend on whether you really want to pursue this later on. In fact, many of you will pursue asymptotic series in many different applications later on, but we will just give you the basic introduction to it. Okay. Any further questions? If not, best of luck for your exam. I will set up give you a problem sheet tomorrow or day after tomorrow. That's more for, well, more for practice if you want. The submission deadline will be after the midterm, so don't worry about the submission. But those problem sheets anyway are going to be a small part of your final results, so don't worry too much about them. They're more important because you want to take a look at what you need to learn for the midterm and the end-sem. Okay, any questions, comments? Okay, so there are no questions. I don't want to really start something entirely new today and just before the exam. So let's call it a day today. Okay. You still have a chance to ask questions if you want to.